Hello, hello. This is part 3 of Unit 11 on gases. So, to pick up where we left off, we looked at several different gas laws like Boyle's law. We saw that as pressure goes up, volume goes down. Charles's law, volume and temperature are directly related, proportional. So, temperature goes up, volume goes up. And Avogadro's law is if the moles of a gas goes up, the volume goes up. And so taking these together, we can have this relationship that the volume is proportional to moles or quantity times temperature, which we're thinking thermal energy, divided by pressure. However, this is proportional to, and what we really want is it to be equal to. So we want to turn this into an equation, so we need an equal sign. And for that, we just need to add in a scaling factor. So if we take this and combine it so that it's PV over NT, what we'll find is that this ratio is always equal to a constant value. And so we give this symbol the letter R. And so this R is just going to have a number, just like if you need to find the area of a circle, you look up pi. But here, if you need to know the volume or pressure of a gas and you measure these other quantities, then you need R. So R, this is for what we're going to call the ideal gas equation. Now, one thing I want you to know about the ideal gas equation, it uses that word ideal. If gases are behaving ideally, it's because they have negligible intermolecular forces, meaning there are no forces pulling or pushing on the particles. Again, negligible just means very, very small, so much that they don't even matter. So this was one part of the kinetic molecular theory. And for a gas to act ideally and follow this equation, then this has to be true. So it's a pretty easy equation to use. The main thing is making sure you're using the right units. So for starters, we need to figure out what the value of R is. So to do that, we're going to set a few standards like temperature and pressure. We're going to set it to 0 Celsius and pressure to 1 atmosphere. And if we do that, if you look at any gas, 1 mole, so 1 mole quantity of any gas, regardless of the identity, it will take up 22.4 liters worth of space. So this is always true. So now if we go back to this gas law and we now punch in 1 atmosphere, 22.4 liters, divided by 1 mole, divided by standard temp, which is 273 Kelvin, then we get an R of 0.082057. And the units are liters times atmospheres divided by mole Kelvin. Now, what's important about these is it tells you exactly what units you have to have when using this equation. So if you're going to put in a pressure, it has to be in atmospheres, not millimeters of mercury or psi. If you put in temperature, it has to be Kelvin, can't be Celsius or Fahrenheit. If you know you have 10 grams of neon, you're going to have to convert it to moles. And if you have some number of gallons, it needs to be in liters. So these units are really important. So to try this out, here we have a sample of sulfur hexafluoride, and it says that we have 265 grams of it at 9,500 milliliters and at 32 degrees Celsius. So all we're going to do is take this equation, and because it's asking for pressure, we're going to divide both sides by volume. So divide both sides by volume, so that way volume cancels on this side, and we get this. So pressure is equal to nRT over V. So at this point, we just need to punch in the numbers and solve for pressure, except we have to convert everything. So we have 265.9 grams, but N, that is moles, M-O-L, moles. So we have to convert first. So I'm hoping after a year of chemistry, you know how to go from grams to moles. And if we were in class, I'd say, it rhymes with molar sass. And you'd say, oh, yeah, molar mass. So we'll use the molar mass to then figure out that there's 1.82 moles of this chemical. R is just a constant, 0.0821. I'll give that to you. You just plug it in. T is our temperature. We're given Celsius. We need to convert to Kelvin. And to do that, we just add 273. And our volume is in milliliters, but we need liters. So just divide by 1,000. And so if you do that, then here's what it looks like when you plug everything in. 1.82 moles. Here's our temperature in Kelvin divided by our volume in liters. We get a pressure of 4.8 atmospheres. So again, we use this gas law whenever we can measure the other properties of a gas, and then we can use this to calculate the unknown. So this is for a static sample of a gas, not one that's being actively compressed or heated up or anything like that. Here's a second problem doing the same type of thing. We have an airbag going off. If you've ever been a wreck, airbags can go off in fractions of a second. I included a video showing it in slow motion. It's kind of neat, but it stems from a chemical reaction of sodium azide, which is thermally unstable. So upon impact, this thing is triggered to decompose, and what's important is it's generating nitrogen gas, because that increase in volume of the gas is what's going to have it expand. So our question says we have 37.5 liters at 80 degrees Celsius at 1.08 atmospheres. How many grams of nitrogen would this be? So we got temperature, we have pressure, we have volume. R is a constant. The only thing we don't know is N. And again, I want you to know that N and grams are not the same. But it's the direction we're going to have to take. So we're going to solve for N by rearranging. N is PV over RT. And once we know how many moles, then we can convert to grams. So we have our pressure and volume. We did not have to convert the units because they were good, atmospheres and liters, divided by the constant R, divided by our temperature, which is now in Kelvin, and we get 1.4 moles of nitrogen. So if this was your final answer and it's asking how many grams of nitrogen would we have, then you'd get it wrong. We don't want that. So going back to molar mass, if we have 1.4 moles of N2 and each mole is 28 grams, then we can now say, yep, that's 39 grams of nitrogen going off in this airbag to save, your face from getting all flattened. Thank you, airbags. And thank you, chemistry. Now, it's called the ideal gas law because the gases are conveniently always equaling this ratio, but sometimes it's not. And when it doesn't, we call these non-ideal gases, sometimes called real gases. Now, for a gas to be ideal, there can't be any intermolecular forces. But when they do start popping in, this is when they are not ideal. So, a couple instances: some gases like sulfur hexafluoride, xenon. Really, there's some gases that are just notoriously really dense. They're going to be non-ideal. Then any gas that, as you increase the pressure, you're increasing the density, it's not going to be ideal. And then low temperatures. So as you're cooling a gas down, remember, eventually it will condense to a liquid, which never obeys gas laws. That's why they're called gas laws. But as as temperatures drop, they don't have enough kinetic energy to just make those intermolecular forces negligible. So what these all have in common is those intermolecular forces are no longer negligible. So the attractive forces between particles starts affecting how they bounce around. So, and this is the case, they are not ideal. They're non-ideal gases. Now, the second way we're going to use the ideal gas law today is called the combined gas law. And this is the one we're going to use if conditions are changing. So we know that we can say this ratio is always equal to this constant. So then we might, I don't know, increase the pressure, decrease the temperature, and we might want to know how does that affect the volume if, let's just say, mole stays the same. Well, knowing that this constant stays the same, we can then set up this equation to see that, yeah, as these two change, how is it going to affect the volume? And so we get the combined gas law right here. P1V1 over N1T1 equals P2V2 over N2T2. So this equation is not hard to use, or at least conceptually. You just plug in numbers. Honestly, most people who get these ones wrong, it's because their algebra skills fail them. So be careful in your algebra. So let's try using it. So first, let's say we have a light bulb we turn on, and the temperature jumps from 18 up to 85 degrees Celsius. We already talked about Charles's law. We would expect that to make the pressure to increase. Now, since it's a light bulb, we already know the moles is fixed and the volume is fixed. So again, if we're starting with this, if we know that N1 and N2 are the same, we can cancel it out. If we know V1 and V2 are the same, we can cancel it out. And we're left with, again, Charles's law. So technically, for any one of those problems we looked at earlier, increasing pressures or decreasing volumes, we can use this one equation to solve all of them, and just whatever is constant, you can just cancel out and just remove it. So now plugging in our numbers, we have our initial to final volume, temperature in Kelvin. We have our initial pressure, and then crisscross, hopefully you can do the algebra, we get 1.48 atmospheres. Okay, let's try another one. So here we have a problem where we're going to say there's a small bubble that's going to rise up from the bottom of a lake. And as you could imagine, like what would it be doing down there? So here's a little video you could watch. I like this little clip. This is showing a lake in Russia that has a lot of methane deposits that build up underneath the frozen lake. And so then for good fun, you poke the ice, release the gas, and have someone light it, and you get fire. Anyway, so let's say the air bubble started under these conditions. So at the bottom of the lake, there's high pressure, there's low volume, and low temperature. But as the bubble rises, temperature increases as it gets closer to the sun. The pressure drops because there's not as much water on top. So how is that going to affect the volume? Now we're going to say N1, the moles of gas in this bubble stay exactly the same. So if that's the case, we can remove it and we're left with this. PV over T equals PV over T. Now, one of the nice things that because we're not using R, we technically don't have to have liters, so we can leave it in milliliters. And same thing, if pressure doesn't have to be atmospheres, but it is in atmospheres. But the only one you still have to convert every time is it has to be in Kelvin. If you see temperature in this chapter, convert to Kelvin. So we have our original pressure and volume divided by the original temperature is equal to the new pressure over the new temperature times the volume. So do this math, multiply by this, divide by 1, and we get a volume of 14 milliliters. Okay, with that, that's all we're going to do for today. What I'd like for you to do is try to work this problem. If a balloon the size of a basketball were to rise up to the top of Mount Everest, which is 8.8 kilometers, that is not relevant to working the problem. It's just some extra fun fact. If this balloon were to rise up and we get the corresponding temperature change and pressure changes, what would be the new volume? Again, if we're going to say it's sealed, we're also going to say that N1 is equal to N2. So you can just factor that part out. So figure out what is the volume. And in the next video on Thursday, we'll start off with the solution. So hopefully you can work this one out. Have a fantastic day.